For linear regression, we had previously worked out two algorithms, one based on gradient descent and the second one based on the normal equations for solving for the parameters theta. In this video, we'll generalize those two algorithms for the case of when we're using regularization with linear regression. Here's the cost function that we're using when we're using regularization with linear regression, where the second term here is the regularization term. And what we'd like to do is come up with an algorithm to find the value of theta that minimizes j of theta. The first algorithm we're going to work out will be based on gradient descent. And so if you remember, for the original problem for linear regression without regularization, we had worked out this rule for gradient descent. And it was written as follows. Theta xi minus yi times xij. Okay, so this is our gradient descent rule, and we would do this for j equals 0, 1, 2, and so on up to n, where n is number of features. Let's modify this to apply to regularized linear regression. Remember, in our regularization term, we penalize theta 1, theta 2, and so on up to theta n, but not theta 0. And so what I'm going to do is first take this update rule and write it separately for theta 0. 1 to n, like so, times xi 0, and then we just cross out 0 here. Okay, so haven't changed anything so far. So and finally, you recall that the way we worked out linear regression is that this term here, this is actually a partial derivative with respect to theta j of our cost function. But now, so this is all this is for unregularized linear regression. But now we've changed our cost function to include the regularization term. And it turns out if you take the partial derivative of our new cost function with respect to the parameters theta j, what you get is essentially the same update rule, except that you have an extra term here of minus lambda over m times theta j. Let me close that parentheses here. And in particular, this new term here, this new thing in the square brackets, that's the partial derivative of j of theta with respect to the setting of the parameters. And because we don't penalize theta 0, the update of theta 0 turns out to be the same. And so if you implement this, you have gradient descent for regularized linear regression. So just point out one thing. If you look at this update for theta j, in particular, you can combine this term in the update together with this term, and the second term is also multiplied by alpha. And so it turns out you can rewrite that update as theta j gets updated as theta j times 1 minus alpha lambda over m, and then minus the rest of this, minus the rest of the usual squared cost function, which I just quickly write down here. Squared, like so. Okay, and notice this is actually exactly the same as the gradient descent update, except for this new term here. Right, so theta j minus, same as the gradient term back there, and this term alpha lambda over m will be, this term 1 minus alpha lambda over m will be a number usually just slightly less than 1, right? If you think of alpha as a small learning rate parameter, or if m is pretty big because you've reduced for training set size, this term here will be usually a number slightly less than 1. And so this is a nice intuition. This is saying that regularized linear regression is just like the original version, except that in each iteration, we take each parameter theta and multiply it by a number a little bit less than 1, and then we do the usual gradient descent update as before. Okay, and so this step of multiplying my parameters by a number slightly less than 1, it has the effect of shrinking the parameter a little bit, and this nicely accords with our intuition that the effect of regularization is it tends to shrink the parameters theta j a little bit. Using this, you can implement regularized linear regression with gradient descent. Let's figure out the other method as well, the one based on the normal equations. So our method for solving for the parameters based on the normal equations was this. We took x transpose x inverse times x transpose y, where x was this matrix that was our training examples stacked together in rows, and y was this vector, let me draw an arrow over that so it gives a vector that had the labels from the training set stacked into a big tall column vector. Now, so this is the unregularized case, right? Now, we want to minimize j of theta as a function of theta. And the way we do that is, we'll try to take the derivatives and set the derivative equal to 0. It turns out if you do this for j of theta being the regularized objective function, what you find is that you get this formula. The derivations again a little bit involved, but I've done the derivations, so let me just show you what the answer is. You get x gets updated as theta transpose, x transpose x plus lambda, the regularization parameter, times a matrix that's 0, 1, 1, 1, 1, 1. Okay, and then the rest of this is the same as before. Okay, and so this matrix here, this matrix I've written in green, this is a matrix with a 0 in the upper leftmost entry, then 1s in the rest of the diagonals, and then zeros on all the off-diagonal entries as well. So just to be concrete, if n is equal to 2, then this would be a 3 by 3 matrix. Then this matrix would be 0, 1, 1, and then zeros in the off-diagonal entries as well. Okay, and this matrix here more generally will be an n plus 1 by n plus 1 dimensional matrix, same as the dimension of x transpose x. And if you implement this, this turns out to be the solution to what you would get if you were to set the derivatives of j equal to 0, and this gives you the generalization of the normal equation to the regularized case. finally, just want to point out one interesting property of that, which is if early on we said that if m is less than or equal to n, so if the number of training examples you have is less than or equal to the number of features, right? Then if you were to try to use the normal equation, then this matrix will be non-invertible, will be singular. It turns out that so long as lambda is greater than 0, so long as your regularization parameter isn't set to 0, it turns out that if you apply that formula that we wrote down, right, it was 0, 1, 1, 1, and so on, x transpose y, it turns out that with this new version, the matrix we have here, x transpose x plus lambda times this matrix, this should take care of the non-invertibility problem as well, and you should be able to invert this matrix, and then it shouldn't be singular anymore. Assuming that, assuming very mild non-degeneracies, that this for all practical problems, this should take care of the problem of the matrix being singular. So to wrap up, you now know how to implement regularized linear regression using either gradient descent or using the normal equations. And using this method, you'll be able to get around the overfitting problem, even when you have a large number of features relative to the number of training examples.